Welcome to my lecture series on computer graphics. Today we will discuss two-dimensional geometric transformations. Now here the object is represented in two dimension. That means any object, we know that any graphical object is basically consisting of a set of two-dimensional points. For example, if we represent a triangle, then we can consider that this triangle is represented with the help of this two-dimensional Cartesian coordinate system x, y, and these 3 points, 3 vertices A, B and C, these 3 points are sufficient to represent this triangle, because if we know these 3 vertical points, vertices, then we can easily generate the straight lines from A to B, B to C and A to C, and this object can be represented. So here our concern is how we can represent two-dimensional object, and we can perform various types of transformations on these two-dimensional objects. Now why these transformations are required? There are many applications where there is a need for resizing the shape of the object as well as the position of the object or the size of the object. For this purpose, we need 3 basic transformations and the combinations of these 3 basic transformations. These are translation, rotation and scaling. Now in case of translation, the object's position is changing without changing any directions. Okay, so if this point is located at xy, if it is translated along the straight line, that means along this vector v, then the new positions of this object is at a dash. Now as we are considering this object is a rigid body, rigid object, that means every point on this object will be translated by the same amount along the same direction. So this b is translated to b dash and c is also translated to c dash, and in the new positions we can redraw the object just by drawing a straight line between a dash to b dash, b dash to c dash and a dash to c dash. So this object is translated to the new positions a dash, b dash, c dash. So this is pure translation. Now let us see how these translations can be represented in computer graphics in different techniques. Now let us consider any arbitrary point. Suppose we are using two-dimensional Cartesian system, because here we are representing every object in 2D, 2 dimension, that means in a plane. So consider any arbitrary point P whose coordinate is x, y, and this point is translated along the vector v, and the new positions is say p dash whose coordinate is x dash, y dash. Now let the x direction translation, this is x direction, this is y direction, this is origin. So x direction's translation is represented by this tx, and y direction translation is represented by this ty, because we can consider that this is x here, this is y, and this new positions x dash, this is your x dash, and this is y dash. So we can easily say that transformation equation x dash is equal to x plus tx and y dash is equal to y plus ty. So the new positions x dash is basically x plus tx, because this is tx, and y dash, this is y dash, which is this is y, earlier this is y, plus ty. So these are the transformation equations. These are transformation equations for translation. Now here two things must be noted. One is this P is any arbitrary point on a rigid object, because we know that in raster graphics every object, graphical object, is represented by a collection of discrete points. So P is one of such point, like P is here, P can be here, or P can be here. There is no need for finding the any point between A and B, because we can draw the straight line between A and B using any other straight line drawing algorithm. So this object can be redrawn in the new positions if we can calculate the positions of the translated point by suitable method. So in this case we are considering any point on the rigid object, and this translation is basically performed uniformly on every point on the rigid object, and these are the transformation equations. Now let us see how those transformation equations can be represented mathematically. We know that any point P in Cartesian coordinate system can be represented by a column matrix as xy. In the same way, P dash can be represented as a column matrix as x dash, y dash. So we can represent these transformation equations in matrix form as x dash, y dash, this is equal to x plus tx, y plus ty. So these are the matrix equations corresponding to these transformation equations. Now we can decompose this as x, y, this column matrix, plus tx, ty, this column matrix, because if we add these two matrices, column matrices, we can get these equations, and left hand side is x dash, y dash. So this is nothing but the transform point, translated point in this case, P dash. This is nothing but the original point, original object point P, and this is corresponding to the translation matrix. Say T, we are considering this V as a subscript which indicates the direction of translation, because from the definition of translation it changes its position without direction or orientation along a direction, along a straight line. So V is the direction specified for this translation. So in this case the transformation equations is just addition of two matrices. This transformation matrix, which is nothing but an operator, that is added with the object point, and we got the corresponding transform points. Now what is the specification for V in this case? V is given as a vector which is nothing but Tx I cap plus Ty j cap, because you know that this vector is sum of this vector plus this vector. So this magnitude is Tx, and I is the unit vector along x direction. So this vector is Tx into I, and this vector is Ty into j, because j is the unit vector along y direction. So from this specification of V, we can easily find out translation operator Tv just by considering a column matrix Tx, Ty, and these are added. So this is pure translation. Now we will consider another basic transformation called rotation. Now in case of rotation, the object changes its position keeping a fixed distance from a point called the pivot point or center of rotation.